You must know the
Um,
formulas.
no, in that textbook I have, there's no cylinders in.
Nah, there must be cylinders, man. Maybe not the volumetric stuff, man. We must be careful. Are you with me? I'm gonna share the
Uh,
formula sheet now, gents, before we move on to for today's session. So we can all be on the same page, obviously.
but I don't have
Most,
the two book, but all the
yeah, I
other
hear you.
textbooks they accept that.
Okay, so you know the thing is what I can recommend. You must go look at the past papers. I must put up a link for you guys, right? Do you guys recall that link for the past papers?
Yeah.
Look from the year 2022 to 2023. Get all that papers and you can see those type of questions. It's straightforward, man. I will not lie to you. I'm just quickly gonna share the formula sheets. I can show you exactly where it is. Um, just give me a quick second. Why am I not seeing this formulas? Oh. Okay, I see it. I see. Let me open it up.
Guys, also, sorry, sir.
Just give me a second. Give me 1 second. I just want to see. Yes, go for it.
Also, the guys who are using Android, they can download the previous question papers on Google Play Store.
Yeah. That's what I recommended as well. I'm just no. Okay, I'm just opening a random paper. That's gonna help. Okay, here we go. Let me share my screen. Why is it opening through Outlook? That doesn't make sense, man. Anyway, can you guys see my screen? This is
Yes,
a
sir.
memo.
That's
Okay.
the marking. Yeah.
Yeah, I'm just realizing now. In 5, 23. Maybe this one. Highly recommend you guys supposed to be solving the
Yeah,
stuff
because I
immediately.
don't see those questions in the 2024 papers.
Nah, it's there. It's there. I'll show you now, man. I just wanna let me just quickly get into. I think I was put in the Google Classroom. What do you think? The formula sheet. Just remind me to put it on here. It is. Where is it? I'm just looking for what I sent. Here's it. I sent items. Okay. Okay. Yeah, I got it. I thought I saved it for some reason. Just opening up. Not it save it. Share. Okay, here we go. Do you see it?
We can see it. Yeah. So
Yeah, so we're talking about those formulas, right? So today's formulas is here, right? This is today's formulas all over here. This is module 4's formulas over here. This is module 6 formulas over here. Here we go. This is, I see, this is not, this is also module, what is this module? What is this? Module, that's a buckling stuff, it's module 6. Yeah, I'm not seeing that volumetric formulas, eh? That's the one you're talking about. Angus.
Correct, sir.
Yeah, so what I'm gonna do now, give me a second. I'm realizing something now, because this I got from a 2019 formula sheet.
it is on the latest papers. The volume and the diameter and the length and.
It's there, right?
Yeah.
Yeah, I don't know what I got a paper now. It's actually good with doing this because I'm realizing now the formula sheet which I've been using is old. I mean, the formulas are kind of, that's not what I remember them. Before we begin, slow him in. Where was this now? Okay, now open him up. My screen is still, you guys can still see my screen, right?
Yes, sir.
Yeah, yes. So can you see there?
At the bottom left.
Yeah. Angus, can you see it? You see him?
Yes, sir.
Yeah, there's it. So it's basically the same, and then they added those pieces here. You
But it's
see?
a 2019 paper. 2013.
2023. Yeah, that's what I'm saying. The syllabus changed in 2022.
I think that one has a more circle question in also.
Yep, it does. So yeah, there's your formulas. Can you see there?
Yeah.
So you'll be sorted basically. Yeah, this is more circle. But more circle, look here, I mean, it's difficult to teach. just online, unless I must really go push for the tools, but if you follow the steps, it's straightforward. Yeah, this is a good paper to go over. I highly recommend this one. It's I mean, covers most stuff. I took some questions here from our last test. I mean, all my tests is coming from past papers, basically. So if you go over a few tests, you should be all right. All right, I think we're done with that. That was a good point. Should possibly I'm just someone with Louis, can just remind me to upload this formula sheet, man. If you don't mind, after the session on the Google Classroom, so we all can just have it there as a unit. All right, so I think we can, without further ado, continue. Is my screen here? Is it on? Can you see stuff moving?
Yes, sir.
Right, so gents, here we go. Welcome back to N5 Standard Material Structures. It's tea time. Just get your pens and papers out. We have to work. Right? Again, ask any questions you need to ask. Yeah, I want everyone to pass the subject. But that being said, you require a lot of work, from what I understand, right? I mean, hard work will never disappoint you. You need to put in the hours. Okay, so just to give you a context again, right? We're doing stencil materials over here, and what we actually looked at in the previous chapters, right, was tension. I believe there's a bit of compression, which is kind of the same as tension, and then shearing, which I didn't really cover, but it's there in your thing. So this first three loads is essentially covered in the first chapter. All right, but if you're not understanding shearing, you should tell me, and I can address that. However, I did post some lectures, which I've done, which can assist you with that quite easily. The concept of shearing, the areas you use is just different. So if you look at the other three, right, this is the other loads. Okay, this is the last two loads which we'll be looking at, and this is a form of stability. But anyway, so this here is the torsion load, where we torque something, which is today's objective. That's module 6. This guy is bending when you bend something. That's module 4. And this buckling here is module 6. Again, as I mentioned to you earlier on, these loads are always present in mechanical structures. That's why we analyze them, right? We put formulas to the stuff. We have formulas. We understand relationships of our variables interact with each other. Same time we can design. Same time we can use it to make decisions. I hope that is clear. So we will be looking at torsion. Next week we'll be looking at bending. Or buckling. I'm still deciding, but most probably bending, right? This is more of a plug-and-play thing, but I'm trying to cover as much ground so that you guys are sorted for, you know, your exams, upcoming exams in December. Anyway, let's continue with torsion, right? Again, it's one of the 5 fundamental mechanical loads. So what is torsion? Look here, there are some assumptions made in the equations, right? I'm not going to go into them. What is important, they say that the shaft is homogeneous, isotropic, and perfectly elastic. Homogeneous means that the material is the same throughout. It's uniform in terms of the chemical structure, but I mean the chemical structure affects the microstructure, affects the mechanical properties. Now, isotropic means that if you pull it in the X direction or the Y direction or the Z direction, you'll get exactly the same tensile strength. In reality, that's not actually true, right? So these equations work with these assumptions. The last one of the main ones, is the Base-Hooke's law. So we're only working in the limit of proportionality. But you guys do not perhaps know, all the equations we're doing is only working within the elastic zone. When you come to the plastic zone, and I'm talking about when you pass the yield point, right? There's more equations. So, but the ones in elastic, it works all right, right? You'll be amazed how much theory there is. Okay. So what is torsion? We have a shaft, right? We're all familiar with the concept of torque, torque wrench maybe. And we're just twisting this thing. So what this here is showing you a piece or an element in a shaft. And it's basically showing you what's happening to a shaft. Funny enough, you can actually see a bit of more, a element which are using more stress circle, which actually comes up at some point. Right though. So they do some formulations, right? I think your textbook derives the formulas for you. Fortunately for you, you don't have to derive anything. You just have to apply. And what you end up with is just 3 prone formula, right? Very important. So I'll talk to each variable, right? So by the way, when we're applying a torque, we are actually inducing a shear stress, right? I hope you guys agree with me, colleagues, right? So can you see there's two parallel forces, right? One going up, one going down. Just look on the sketch on the right. Can you guys see that? I hope you guys can see that. And in essence, you induce a shear stress in the shaft, right? So what's all the variables when we're looking at analyzing a torsion, right? Which is one of the loads. This guy over here is called the shear stress, right? That is not the same stress as your tensile stress, etc. You know, that's a different type of stress. It's a shear stress. We have R, which is the radius. We're all familiar with that. T, which is the torque. That's the loading. Instead of a force, now it's a torque. We have J, which is a very important property called the polar second moment of area. What that property is, right? Number one, it's a function of the dimension of whatever you're looking at. So what it means is that whatever shape, whatever geometry you have, the polar of second moment would be different. So for shafts, there's one formula, right? Pi d4/32. Just be aware. So again, what J actually is for, the bigger J value or the polar second moment of area, the greater resistance to torque. I'll say that again. The bigger J value, the greater resistance to torque. So if you increase your polar second moment of area, your torque will drop basically. Your thing will resist the amount of torque. It's in essence making it stronger. Then that's equal to G, which is your shear modulus, right? Or your modulus of rigidity, which is, it's kind of the same as your elastic modulus, but this is now for torsion, so G. Then you got your theta, which is your angle of twist. Can we all imagine the angle of twist there? So you start over there and you twist it, right? It's like a strain of some sort. I don't know if you're with me. And then we divide that guy by L, and that's the length of the shaft. In essence, this is like the strain type formula. But this three-prong formulation is what you do to analyze in this whole chapter. So it's very important for you to, you know what I mean, understand what's going on here. I'll come back to these formulas. It's in your textbook. They're actually showing how to get it. So what I wanted to talk about was the polar second moment of area. Once again, as you can see on the screen, in particular in this column over here and that column over here, is that they all have different polar second moment of areas. And what's important, it depends on the shape, right? So if you have a different shape, you have a different formula. And again, the bigger the J, the bigger the resistance to torsion or deformation or deflection, whatever you want to use. Are we all on the same page, students? Any questions?
Yes, sir.
Okay, so without further ado, let's begin our first question, right? So just I'll give you 2 minutes, and I'll prep the whiteboard so we can begin. Okay. So again, just get the textbook out. Obviously, ask questions. You know how it goes. Let's have a look. Let's have a look. Where's this question again? Tell me, is everyone, did everyone study through Northlink, or is some people new in the game here? I'm just curious. Are you guys all part of Northlink, or is this like one subject you're taking, or what's the Camilla, Mangaliso, Mr. May? Angus, sorry?
I'm studying through Northlink.
Oh, okay. Okay. Are we ready?
You can go ahead.
Okay, so we're gonna solve, right? Do you guys see my question there?
Yes, sir.
All right, so here we go. So again, it's obviously easier if you go over the stuff, if it's easy for us to kind of solve. Now, I'm gonna ask a quick question, right? Is anyone familiar with the formula for mechanical power? That question there, that power transmitted. Does anyone perhaps know the equation we use to calculate mechanical power? This one. Power. Yes, Louis, talk.
No, it's fine. Isn't it that 2 pi nt over
100%.
60?
That's the one, yeah. Essence is actually torque times omega, right? If you ever wondered how they get the power of an engine, right? You know what I'm talking about? A particular engine. They'll take a torque at a particular speed and they'll rate the engine at that torque. Louis agrees with me?
Yes, sir.
Yeah, that's it, right? Or obviously you can put in a dyno. I'm not sure what they're using nowadays, how to measure power and torque on the engine. And you can do it experimentally, obviously with a dyno. I think that's covered in Power Machines in 6, where there's a whole setup on explain that. But this is mechanical power, right? This is what the mechanical engineer cares about. This is mech power. You might be asking why is it important? Because you also get electrical power, right? 3-phase, single phase. So this is 3-phase, cos phi. It's also in kilowatt, right? This is hydraulic power, right? Though you see, this is hydro. It's for fluid. This is for electric. A good engineer should know how the powers are transforming into each other. Yeah. Am I showing off here, or I'm not going to show off? But yeah, you get also chemical type, which can produce. If you have this is a mass flow, the mass flow rate. This is also heat power, right? This is due to heat loss or heat gain in kilowatt per hour. Change in enthalpy, right? That's also, yeah. So in each chapter, actually, you can actually compute all the different powers and actually put them together, right? But anyway, so we're looking at mechanical power. Just showing you that that's a formula you must use there. So let me just erase this and begin with today's bread and butter. Let's read the question. A 50 mole shaft with a length of 1.1 meters. It takes 800 revs per minute, and the maximum torque in the shaft is 12% more than the mean torque. Very important. The allowable angle of torque for the shaft is 2 degrees, and the modulus of rigidity is 95 gigapascals. Okay. They need to find the power transmitted. So we need to say power is going to be equal to torque times omega. Okay, that's the first thing. But we have omega, which is the rotational speed. We need to compute the torque. How do we find the torque, students? Let's quickly see. So you use that formula what I showed you. The T over J equals shear R over G theta over L. Again, it's in your formula sheet, right? I'm going to paste it for you so you can just quickly see this one. Okay, are we all on the same page? Hence, students, can you see that? Today's meat and potatoes. Are we happy? I don't know if you're thumbsing up or what, I can't see it. Mangaliso, Sumila, can you guys see that? Sure, thank you.
Yes, sir.
Thank you, guys. Okay, let's begin. So, we need to find the torque so we can compute the power. So how this typically works is you must look for whatever knowns or data is present in this particular thing. So based on this, I can see a G, right? A G is there, a theta is there, plus we have a L. So obviously this here would be the one. Then we need this side here, right? Because then we can equate this side and this side together. This is how it works. So you have to look at what you have and then equate whatever you have together, typically. So let's quickly do that. Here we have T over J, and this is G theta over L. Okay, so these three things are given over here. Okay, So now we must calculate this J, right? So J, I'm going to put it here. You know, obviously I'm teaching you and kind of doing a quick tutorial. I'll show you where the J is, man. Okay, I'll in your formula sheet. Well, I don't see the normal J, but anyway, it's like this. It's gonna be J equals pi over 32.
I only do the one for the hollow on the formula sheet.
Yes, did the power 4. See, Louis has got it. So if you have a hollow shaft, this is for solid. For hollow, it's gonna be pi 32 big D minus small d to the power 4, like that, right? So Mr. Lou Furi said that they only put up the hollow there, but the solid one you can easily remember just based on that piece over there. Okay, so we must now compute this J, right? So J equals pi over 32. Once again, this is the resistance to the torque, and my diameter is 50 mil, 0.05. Okay, to the power 4. Okay, so what is my J? Talk to me, guys. I'm hoping we can cover everything today, but yeah, I doubt it. Amos is time to join. Okay, so what is my J?
6.137 times 10 to the power -7.
Okay, just give me a second. Right. Just give it to me again.
6.136 times 10 to the power -7.
Yep. And the unit here is going to be meters for, right? You can see over there. So once that is done, it's torque divided by J equals G theta over L. And we're looking for the torque. So G theta goes and L go here, and we times it by the J. So the matter of just putting in values now. So my value here was 85, if I remember correctly. Just want to get my book here. Easy to write. This is the easy chapter, but it can also become a bit. There are some sticky problems. G was 95 gigapascals. There we go. Shoot the gun. And now we need to. I failed to mention something. We have to put degrees here, right? But we don't put the angle in degrees. The angle must be converted into radians. So to convert into radians, I'm not sure if you remember, it's the degrees times pi over 180. Right? It should be 2 pi. It should be pi over 180. Yes. Okay. Why am I saying 2 pi here? Doesn't sit right with me. Yeah. And 180 for pi. Yeah. So 2 times pi over 180 will give me something radians. Okay. This is in rad. So our angle, are you all familiar with the concept of radians? Students? Who's not familiar with the concept of radians? That's going to be 2 times pi over 180. And we should get an answer of 0.035 times that there. Should be correct. Our length was 1.1 meters. And then we must times by J, right? So J, I'll just quickly remove this here. J is gonna be the, you said it was how much again? Look at this. It was 6.13. Okay, 6.136 times 10 to the negative 7. All right. So what do we get for the torque here, guys?
1.85 Newton per meter.
Okay. Yeah, it's kilonewton meter, not per meter.
Oh, sorry, man. Kilonewton meter.
Oh, it's fine, it's fine. So it's kilonewton meter, right? I believe that's correct. Can we all corroborate Louis' answer?
It's correct, sir.
100%, yeah. Okay, right. 854.75. So that's our torque, right? So like I said, we're not done yet. We need to now compute the power transmitted by this particular shaft, right? So power equals 2 pi nt divided by 60. Put in the 2 pi, we put in the 800, we put in 1.85 times 10 to the power 3. You must know it's kilonewton. And we divide this guy by 60. How much mechanical power do we get? Let's see. And we're going to come back to the question because they are talking. Okay, this I should have done before. Let me do this first. So before this, guys, right? I realized the question did ask for the maximum torque in the shaft is 12% more than the mean torque. So when we calculate this here, this is actually the mean torque, right? The average torque. But we need to now get the maximum torque. That's what we actually need, right? So to get the maximum torque, it's 12% more. It's quite easy. T max is equal to T mean, right, times 1.112, right? This is the same as saying T mean times T mean times 0.12, right? Because remember, we're increasing by, plus T mean plus T mean times 0.12. You're just taking T mean as a common factor and you end up with this equation. So we need to compute the maximum torque, right? So if you find the maximum torque, you should get it 1652 Newton meter. And that guy you put in here. So typically the question wants you always to compute the maximum torque, but it depends on the nature of the question. So again, just be conscious of the mean and the max torque.
So,
yes, go for it, man.
Isn't the torque that you worked out at 1.85, isn't that the max torque? Is it? I'm just asking because the way the textbook break it down, that's max already.
Yes. I'm looking at it now. This is less. This doesn't make sense. We are just give me a second. So this here, right, is the this is the max torque here. It's something that this thing is something's about, yeah, anyway, okay, it's fine. I'll set it like this. Yeah, this is the max torque. Sorry, this is the maximum torque. It makes sense. This is the maximum torque this thing can handle. But when you put in the power formula, we're looking at the mean torque. It's sounding uncomfortable to me for some reason. Okay, it's fine. I'll go with the structure of the textbook. So therefore, I'm wrong here. And then this must be 185 kilonewton, 1.85 kilonewton. And we must now find our T mean. So we have to divide by the 1.12. So that's T mean equals 1.85 times 10 to the power 3, and it's 1.12. Yes, okay, no, it is correct. They're right. I'm just used to a different way of questioning. And we should get 1652 basically Newton meter. And the mean torque must be less than the maximum torque. Yeah. So we take this guy, we put it in here, and we compute this power. Colleagues, what do we get for this power? Damien. Van my. What do we get? Liso.
We get 138,
Yes.
398.
Yeah. 398. Yeah. So 138.398 kilowatt. Perfect. Okay.
Yeah.
So I'll be clear again. This formula yields the maximum torque. That is correct. It is correct. I made a mistake definitely. And then you need to find the mean torque, which essentially is normally in the power formula. What I'm used to is normally using the mean torque. From the mean torque, I get the max torque, and then from the max torque, I actually I go backwards. So yeah, I think I'm so used to that type of question. So yes, this will yield the max, and you have to find the mean. That makes sense to me. All right, so we did 2.1, and then we have to compute the maximum shear stress in the shaft, right? Again, this is important because it'll tell us what material we must use, right? So we need to choose a suitable material based on this value. So if you look at the formula again, we have shear over R. You can use either shear over R, shear stress over R on this side, or you can use this side or that side. It's entirely up to you. Remember, the ratios are all equal to each other. So we can use shear R, and we can use maybe G theta over L. Like I said, you could have used torque over J, but I'm just using that other side deliberately. Okay. So shear stress is, I'm going to show you two different ways though, is G theta over L times R, right? So this guy was 95 times 10 to the power 9. This was 0. What was it again? 0.035 radians times R. Basically, R is our radius, and you're dealing with a 50 mole shaft, so therefore that's 25 mole. 0.025, and then we divide this guy by a 1.1. And can someone quickly compute my shear stress? Your answer should be in megapascals.
It's 71.25.
Okay, 71.25.
Yes.
Okay, slightly different answer. Am I using the right values there? 0.035 times, yeah, it looks right to me. Everyone agree with this answer?
No,
Okay,
so I'm getting 75.568.
say again?
75.568.
568. Yeah, this is close to the.
Oh, okay.
Yeah. Mangalisa, I don't know if you see a mistake or what.
Oh, I see my mistakes.
Yeah, that's 568. Yeah, for sure. Yeah, that's fine. That's good enough. The answer should be this. Yeah, this one over here, not this one. That's our shear stress. Now, this is one way of doing it, but if you look at your formula sheet, right, they give you some nice relationships you can actually use, which I recommend you use. So this one is the torque of a solid shaft. So what this basically is, and I want you to do it now. You see this formula over here, this one? They basically put it in terms of diameter, they rearrange it a bit, and you end up with this formula over here. Sorry, not this formula, they use this one. T over J equals shear R, and they just basically manipulate it, and you get this formula. This is what you probably will be using the most. So I want you to use this one to solve for your shear stress now. Let's see what we get. Answer should be quite close. Are you with me, colleagues? Do you understand what I mean? Guys are quiet, man. Angus? Formula?
Yes.
Yeah. So again, I just use that one.
Yeah,
and just-
what you
Great. Don't be silent, man, please.
was it driving?
Oh,
Traffic now.
okay. So I'm like a basically like a radio presenter here. Okay, so just check this formula and then compute that torque for me. I mean the shear stress. So you just wanna say torque equals pi over 16 shear du cube times torque times pi over 16. You divide that guy by d cubed, and you should be able to get your shear stress. It should be, if not the same, it should be close at least because of the rounding off and so on. Pi over 16. What do we get?
Yeah, it's the same. Sir.
Yeah, should be the same, right? Okay, so this is probably the one you're gonna want to be using anyway. Can everyone confirm that? Okay, can we confirm? Before we move
So
on.
this one we're using the maximum torque.
It should be this. Yeah, it should be the. Sorry, the. Yes, the maximum torque. Because it's based on this formula over here. Yeah, it's this one. You should be using this torque over here. That's correct because it's in essence the T over J. Yeah. So you should have 1.85. Pi was 16, and then you divide this guy by the 0.05 cube. Yeah, that must be the maximum torque. That's correct. The mean torque only comes into play when we come to the power formula, man. My calculator is battery must be changed. Q. Why am I getting a different? Why am I getting a different
Yeah,
answer?
I'm checking 3 times now. I'm getting a different answer.
Yeah. It shouldn't be. I'm missing something in my formula here. Guys, you wasn't trust me, eh? It's this here. It's times 16 first. My maths times 16, right? It's first times 16, and then we're dividing by pi, then d cubed. Not that. That's the mistake, man. So yeah, fix that. Sorry. Yeah. And if I'm wrong, you must please tell me. Yeah, the answer is 75. 75,37 as per
Yeah, it's
textbook.
more or less the
there we
same.
go. Yeah. Should be this textbook as this one. I don't know exactly where we're out here. Come on, guys. Come on.
That formula is for
Yes.
solid.
Yes. Thank you, Louis. That's for a solid shaft. Yeah.
I just want to make sure I didn't write it down.
Yeah. So I'll show you. This one is for. It's in your formula sheet. So it's just like we have. Where's this one? You know what I mentioned to you about the hollow? Like this, right? The torque, which it's the same as this one, is going to look like this over here. I'll paste it now. So that same formula for a hollow shaft, right, will look like this. It's basically the same, just for the d to the power 4.
Okay.
Yeah, you see, this is very important because One of the favorite questions in the exams that I've seen is that when they're asking you to compute, even for your upcoming test, you must know how to basically ask you for the dimensions of the hollow shaft, man, given a certain amount of torque, whatever. But they'll give you the ratio between the small d and the big D. So this is for solid, torque for solid, torque for hollow. Has anyone worked with hollow shafts before? Anyone? Anyone? No one?
No one.
Okay. So how did we find that one? Was it easy? Straightforward? Was it easy? It was difficult, you must say. Challenging? Okay, no one is saying anything.
Not that much, not that much.
Yeah, it's okay.
It's understandable.
Yeah, I know it should be. I hope so. So let's incorporate the hollow story now, right? So I'm gonna skip example 7.2, 7.3 because that's fairly easy. Yeah, it doesn't seem like a big problem. But we're gonna move a bit away from the solid shafts and we're gonna move to the okay, let me give you a small test, man. You know, I'm sure you're able to do this one. Now I'm gonna quickly leave this here, but I'm gonna put up, right? So I want you to use this formula, the one I just mentioned now. This one here, this one. Just wanna copy to solve these problems, but no man. But I wanna put up something. Okay, anyway, try it first. First try it. But let me just okay. Then we can do the next example. Okay, this is not. Oh, there we go, sorry. Yeah, use this one. Right, so I want you to just quickly solve. This should take you less than 5 minutes. Just quickly solve this one. A, B, yeah. So I want you to use that formula to be comfortable with that one. You're gonna see a nice ones. It's basically okay. Another one. Okay. Let me know when you're done. Excuse me? You want to get it? Melissa, what did you get? Damien, are you guys here? Are you guys working? What are you guys busy with? Okay, I'm going to paste something here. And I want to quickly articulate something. So, the shear stress basically is a function of the radius, right? So what I mean by that is that as you increase the radius, the shear stress gets more. In fact, it reaches the max. The value you are computing most of the time is at the peak over here. Okay. So at the center, there is no shear stress because there's no radius.
Yeah, trick question.
Yeah, that is the point, man. So the higher that it goes, basically, the more you get. So in this case, it will be 0 megapascals. Okay. And they're asking for a radius of 20 more. So then you must use this formula over here, you see? You just have to work backwards, basically. Because they give you the torque. Yeah. No, not that. Yeah, I'm right. You have to work backwards. So that's going to be easy. 200 equals, are you guys working this out or what's going on? Times, I'm saying 0.04 now because it's the diameter times shear. You compute your shear and you should get around, let me just calculate this guy.
15.9 megapascals.
Okay, 15.9 megapascals. Just going to calculate him. Power 16. Is everyone here? Just a
Yes, man.
just a warm up. Just one to play. And then last one for a solid shaft. Yeah, 15.9155. Another 5. And then for B, sorry, this was, yeah, you know what I mean. For B, also easy. In this case, they're giving you they give you T max, T, and this is pi over 16 D cubed times shear, right? And now they're giving the shear stress, and now they want to know D, which is a very important thing. So basically, what this is, we know we're loading this car of 200 Newton meter. We need this amount of torque, let's say on the engine, or we're transmitting this much. Pi over 16, right? Then we have dq, and then we have our shear of 80 megapascals. This is a type of calculation where we now basically have to find some more of a design calculation. So we know how much torque we're giving, we have the material, and now based on this calculations, we are going to determine what is this? What size shaft we must purchase or procure and put it in. I don't know if I'm making any sense here. That's 200 times 16, and then dividing by the pi and the 80. So this is the shaft we must go and go buy. Because now we've decided this is our system, and this is assuming this will make us a shaft won't break. You choose a different size shaft, it will snap due to torque. You guys with me?
Yes, sir.
Yeah, it's just not numbers. Decisions. Right. So what is that D for me? What do you get for the D?
I got 23.35 millimeters.
Okay, are we all happy with that? That sounds like a shaft. Okay. That's definitely on board a ship. 23 more shaft. That's quite small, actually. Maybe a toy car, whatever. I don't know. It's only 200 Newton meter of torque. So we all get that? Colleagues? Can we move on?
Yes, sir.
Thank you very much. Okay. I'm not sure if you guys are learning anything or I don't know what's going on. Do you guys go over the examples already, or I don't know. Just hope God can come in here. What he must do. So example 7.4. Right, this one's a nice one. And I want you to now to come in here as well. So this is a good one. So this one, they want, so now we must we have to design our Hollershof. So Hollershof needs to transmit 3000 kilowatts. That's a lot of power. At 120 revs per minute. To give us the ratios of the diameters, and the shear stress may not be more than 60 megapascals. So they determine the diameters needed and the torque per unit length. So here they want us to now compute the diameters, right? So the first thing we must do, and I want you to quickly do this, is compute the T mean. This is what I'm used to, right? So P equals 2 pi N T mean over 60. I want you to find this for me. Please do it. Once we find T mean, we must then now find T max. But I think in this case, T max is equal to T mean. Right? So just be aware that normally find T mean and then you find T max and then you design the shaft. Okay, so once you do this, you find T mean. Now remember what I told you, there's another formula, right? For torque in a, once again, torque in a Hollershof, right? So that formula looks like this. I'll paste it here. So I want you to quickly just get me the T mean quickly, if you don't mind. I recommend you actually go over this, do it. So you're doing the push-ups now. All right, so you're gonna first find T mean here. I'll wait on you guys. Then I can show you how we're gonna sort this guy out. Thank you. Anyone with the T mean?
It's 238,
Yes.
73
Okay, 73. Newton meter? Kilonewton?
kilonewton meter, yes.
Yeah. You can already see here, we require big torque for that amount of power, which makes sense, right?
Yes.
So in this case, we have T mean, right? Normally you have to find T max now. So I'm just giving you the standard story. In this case, it doesn't happen. So we are assuming our T mean is with T max. Once you have this, we must come to this formula. What I'm doing here is very important, right? This is a standard thing in your exams, even your tests coming up. So with this, we now have to equate this, but now we're looking for diameters. But they say there the ratio of diameters is 3 to 1, right? So they're saying big D must be 3 and small d must be 1. So therefore, D is equal to 3 times D. So our small diameter is basically, our big diameter is basically 3 times the small diameter. So there we have a ratio. Okay, what you then can do is put it maybe in terms of, maybe it depends what you want to put here. So if you want, I think we already have big D, so we want small d as a subject of the formula. So then we're going to say D over 3 equals small d. And 1 over 3 is basically 0.33. That's a third most. So that's going to be 0.003 d equals small d. So we're taking this guy and we're putting it in there. So first thing, our torque was 238.73 kilonewton meter. Then we have pi over 16 times your shear. It's 60 megapascals. So they gave us, so we already know the material. And now you must substitute. So big D, we already we're looking for. Small d is, remember, 0.333 big D, but in this whole guy, whoa. This whole guy over here is to the power 4, and we divide this guy by D. Okay, so then let's quickly solve this. So what we do now is 238.73 times that. And we're dividing this out by this. So it's pi over 16 times 60 times power 6. And then we're left with a big D4. Right, I need to find that for me. And then minus, it's going to be 0.333 to the power 4. And then we're going to have another D to the power 4. See there? Maybe you guys can see that there. And then we're just gonna divide that by D. Okay. Let's see what we get. What is that thing equal to there on the left-hand side of the equation? Welcome, by the way, welcome to Info Standard Materials and Structures, eh? Welcome. I didn't welcome you, here you are right now. Deep in the hornet's nest. So let's quickly find that left-hand side. Damien, you quiet? Aiden, you quiet? Mohammed, you quiet? What's going on? That was saying.
Actually, I'm just listening. I came a bit late, so I'll just go through it again. So I'm just
Okay.
now.
Right though. So Mila, you got it. What is that? What is that side there? Okay, so while you guys are finding that one, on this side, we can divide both sides by D, and here we have D cubed minus 0.3334 D cubed also. We take D cubed as a common factor. We're going to have 1 minus 0.333, is it 0.33 or 0.33 to the power 4. So whatever we have on this side, we divide by that over there. Yes, I'm listening.
I'm getting 20.26 4 times 10 to the power negative 3.
20.26, no?
Yes, sir.
Like this, right? That's fine.
Yes, sir.
So then once you do this, now you must divide by this piece over here, right? And then you're going to have D. I'll write it out like this for you. You can obviously do the rest for me. 20.26 times 10 to the negative 3. 1 minus 0.3334. Obviously, this guy must be cube rooted. Now, I wonder if someone does this in a part of their job every day, besides a shaft. I wonder if this is worthwhile doing. Yeah, tell me. Okay, so give me the D. Remember, it must be cube root today.
I got 273, what's this, 76 millimeters.
On the dot or what?
No, I rounded it off. It was a 7579. So I just made it 76.
Okay. Do you agree with Dr. Fourie then? Just gonna confirm that one. I'm missing this. Yeah, 73739. I get, yeah. And I get 273739. That's what I get, yeah. I get, yeah. Especially that I get 73739. What do you mean this? Okay, that should be it. And then if you want your small diameter, that's D equals what? 3 times D. So therefore we take the answer divided by 3 and we should get 91 something, right? 91.25 maybe, approximately there. And there we designed our shaft. Are you all happy with that? Who's happy? Mangaliso. Also, Mila, your mic is on. Muting. Is it you or Mr. Ishmael? Is it Hossein, right?
Yes, sir.
Okay, right. So that's in millimeters. We got this. Okay. And then the last part of the question, it's asking for and it was per unit length. I do not know why one would ever need to know this in a practical sense. Then again, I don't design these things. I've got 2 formulas for you. I need to try one. So these formulas are formulated for the angle of twist being the main variable. I want you to just quickly use this one. So this one, obviously, again, is for the solid. Obviously, you can see it's 1D, and this one is for the hollow. So what I want you to do, just plug in those values for me and see if you get that angle of twist per meter. And remember, it's going to be 1. This will be 1, basically. That L will be 1, if you think about it. Am I correct? Yeah, it'll be per meter. So you could just say 1. You see what we get? Just hope it's going to work out. Guys, can you guys hear me?
Yes, sir.
Yes, yes. Can we move on? I don't know. I think my mic was muted the whole time. You guys are not saying anything, but do you guys manage to get the theta?
I got 5,55. Not sure if it's right.
Yeah, it's correct. Yeah, so it's 5
Times 10 to the power minus 3.
Yes, it's 5,55 times 10 to the power -3 rads. You guys are not saying anything. I'm talking here. Rads per meter. And obviously, if you want to convert this in degrees per meter, you're just going to times this by 180 over pi. So I'm just mentioning that this and this thing is the same thing. That's what I was talking about. I thought my mic was on the whole time. Is there any questions? Gents, say something.
No questions from my side.
Okay, so what I'm thinking now, when you guys writing again, just remind me on Wednesday, right?
Yes, sir.
And who's writing on Thursday? Just remind me.
Chaka, sir.
Who?
Chaka.
Oh, Chaka. Oh, you. And on Monday, what's happening on a Monday? Anyone?
Writing also on Monday.
And
Tuesday
Angus,
writing also.
Angus
And
is writing
Angus.
on Tuesday.
So what I wanted to do, if I'm not gonna and what's happening on a Thursday? You're also writing. Who's writing on the Thursday?
Chaka, sir. So me.
Okay, so what I wanted to perhaps do in preparation for your next test, maybe is to meet you guys on the Tuesday, you know, or whatever, I don't know. And we can move our session from the Thursday to the Tuesday, so I can support you guys, you know, in preparation for your test. I don't know if that is something you'd like to do, or I don't know. What is your recommendations? Because our time is up. What do you guys suggest, Louis? Chaka?
On what day we are writing, sir?
On the Wednesday.
On a Wednesday, the thing is, I'm doing 4 modules, so I'm writing the whole week
Yeah.
up until Thursday.
So I don't know what the other guys.
But say, what you can do, you can go with the class, then record. Then I will watch later.
Yeah. So I think what I'm proposing is I can do the normal Thursday, and but I'm also thinking of if I can have the Thursday session earlier, because I believe I don't know how your marks work with these tests. I don't know, like how much does it weigh in terms of the total mark? How much does your final mark weigh?
This one is 70, sir, and the first one I think was 30.
30, right? And then your final?
This one, sorry, the one we're writing next week is 70% of our what you call it, our term mark, basically the fine. You just write these two tests to qualify, basically to write the final.
Okay. So my question is the final something separate from qualifying?
Yes.
Okay. Okay.
So test one was 30%, and then the test next week is 70%.
Yeah. So that's what I'm proposing. I'm happy to meet on Thursday as a usual slot, because I'm also realizing we didn't cover everything. Because now I want to do shafts in series in parallel. But yeah, that's my next thing. I want to do it with you. I actually want to do it with you. So I don't know how we're gonna do it. But what I do recommend for my test, the test coming now, go look at the 2019, 2020, 2021 papers. But start with 2019. And then look at and then also look at so this is from 2019 2021, and then also look at the 2023 to 2024 papers for this up and coming test. I believe you guys will all qualify, but that's what I recommend. Go over all the questions you can go over. But yeah, I don't know how you guys would like it. If we meet Thursday, no problem. I'd like to continue with torsion and finish and do it justice. And then we can move on to a bending. But for sure we're not going to touch everything. I can already see it's impossible. Literally impossible. But okay, guys, thank you for a good session. I'll see you next week. Please, if you want a session before your test, please let me know. Let me know by the Monday. You know what I'm saying to you. And maybe we can do it a Tuesday. You know, so that when you come into Wednesday, you can have something to extra to look upon. And if you have any additional questions on that session, are you with me? Then you can actually ask in preparation. So I can actually assist you so you can qualify for your test. James, is there any last comments before we close shop? Louis, Angus, Chaka, thank you, Mangaliso.
Yeah, sir, I will ask questions once I've worked out all the stuff and look at all the stuff. And whatever I start with, what I will.
Yeah, James, you need to push on this one, man. The subject is really demanding. It's extensive for the numbers if you're not good with the numbers. But like I said, let me know. I want you guys to let me know. Let me know on Monday if you want a session on Tuesday. Then we can do a session earlier. Then we can do it in preparation for Wednesday.
I think I think it also depends on what session the people are writing. If they're writing at night or in the afternoon, because there's two, if I'm not mistaken.
Yeah, so it's fine even if they're writing, but then at least
Can record it.
There's a recorded, yes, and if they have particular questions, they can so much just ask on the group before, and then when they prepare, at least they can know. But like I said, the preparation, what I expect from you guys, 2019 to 2021, 23 to 2024. That's all you must go over. Go over those stuff and you'll be sorted. Right, guys, gents, thank you very much, and I'll see you next week.
Thank you, sir.
Cheers. Thank you.